So pre-calculus 20, McGraw-Hill Ryerson, pre-calculus 11, textbook right here. We are entering into chapter 9, so this is section 9.1. We've been talking about, in chapter 8, we've been talking about solutions to systems of equations. So where we have two lines, or maybe a line and a parabola, where they intersect often represent solutions to various types of problems. But there's usually one or two solutions there for an intersection. And that's basically where you have two equations, okay? If you have two equations, first of all, an equation is a set of points that satisfy the mathematical description that the equation describes. And so you have a certain set of points on the line or on the curve. So if you put two of those together, you're going to get one special combination of points that is the solution to the system. Now, in this chapter, we're talking about not equalities, we're talking about inequalities. So think about it this way. We're not talking about the points that are on the line. We're talking about all of the points that are either above the line or below the line. So we're talking about a range of values, not one specific value or not one specific set of points that equals, okay, that it's on an equation. So what is that? How does that translate? Well, if you're talking about, if you're an engineer and you have, you're building a structure of something, you have a certain tolerance of how much this structure will be able to bend or be, what's the word? I can't even think of the word right now. But there will be a deformation, okay? There's a certain range of deformation that is acceptable for structures. Like if we're building a bridge or something like that. So in a bridge or a building or something like that, there is an acceptable amount of movement. I don't know if you guys have ever been on a tall structure in a wind. Like it can move, and that's okay. Buildings are not so rigid that they can't move, especially buildings that are built in places where there's earthquakes and stuff like that. There has to be some kind of flex. Buildings actually flex a little bit. So there's a tolerance, there's a range of solutions, and that's what inequalities will help us to understand and to determine. So a couple key terms that we're going to study: solution region. That would be sort of where there's an area of solutions. All of these solutions, all of these points in this area would actually satisfy an inequality. The boundary would be sort of, well, it's literally the boundary, which is actually the same as an equation that would form the line that is the boundary for these regions. And then we'll talk about test point here right away. Okay, so 9.1. Okay, linear equalities in two variables. So what we're studying in 9.1 is we're going to explain when a solid or a dashed line should be used in the solution to an inequality. And also explaining how to use test points to find an inequality, sketching and solving problems. Okay, so let's first of all talk about this, pulled from your textbook here. You might want to just jot down in your own words what these mean, or jot this sketch down. But first of all, an inequality it looks like an equation. So it might look like something like this: y equals mx plus b, or in a different version, different form, ax plus by equals c. It kind of looks like that, but you notice something special, that the solutions are, represent a region. They form a region, a whole area on the coordinate plane. So it's kind of like this right here, except we're saying let's figure out where we have points that satisfy the inequality instead of the equation. So notice here, as I just jotted up here, this is the boundary line, and that is the equation. Okay, so the equation of the line is the boundary. Above that, or in one side of it anyways, usually above, is where this part of the equation is greater than the constant. And again, you're going to have to use test points to figure out exactly which side of the line matches with the inequality. Okay, but this is one region that's acceptable, and for this case, it's this inequality. This region down here would satisfy this inequality. And again, the inequality is based on the equation of the line that forms the boundary. So the solution region would contain all sets of points that satisfy the inequality. So think about this region as millions and millions and millions and billions and trillions of points that are all solutions to an inequality, where we have an inequality, not an equation. And then this is known as the solution set. So maybe we need to review this. If you have something that looks like this, that is less than, okay? Less than. This is greater than, right? Greater than. This one right here, where can I draw this? This one is less than or equal to. And this one is greater than or equal to. So you see the two different types right here and right here. When it doesn't have the little line underneath, that means it's not equal to. So the lines that are on this, the boundary line or the boundary curve are not included in the solution set. So that's these ones, where there's no or equal to. It means strictly above or below the line. These ones would say above the line and including the line, but these ones down here would say just above or below, not including the line. Okay? Okay, so that's where we're starting. That's where we're starting with this sort of concept. Now, we're going to do this right here, graph this line. So I want you to write this question out. So here's our example. Okay, example 1, let's say. And we're going to graph this line right here. And this is the form that you'll see it in often. So we're going to do this from scratch. So take a moment to just write down that question. All right, so first of all, probably what's going to be easiest. Now, you don't have to rearrange this equation. You don't have to rearrange it. You can just do a table of values. So this is assuming we're going to do this without a graphing calculator right now. Okay, so you don't need a graphing calculator, but you can just, what you could do is you could find the intercepts or just put some points down there. This is a straight line, right? Because it's got no squared on the x or anything, so it's not a parabola. It's a straight line. So you could just go ahead and generate 2 or 3 points that you know that are on the line, and then you could start by plotting what the boundary looks like. That's the important. Plot the boundary first. So I'm going to say if x is 0, what is y? Well, 2 times 0 would be 0. So then I have, and again, I'm putting points on the equation. So you want to test, so you want to find points that would be on the equation, the equal sign part of it. So if we have 0 plus 3y equals 6, y is what? 6 divided by 3 is 2. Okay, we have 0, 2. Well, what would happen if y was 0? Well, then we have 2x plus 0 equals 6. So x equals 6 divided by 2, or 3. Does that make sense? Does that look good? So again, you want to plot the boundary first, which is the equation. So I'm going to put these 2 points on the graph here. So 0, 2, that's 0, 2, that's this point. And 3, 0 is right here. X and then y. All right, so with a straight line here, you're going to connect the 2 dots, right? And for some reason, my pen is white here and really thick, so I'm going to change that real quick here. Pen properties. Let's go green or something. Okay. So you're going to want to just you want to draw a line there and connect those points as best you can. Okay, with a ruler, a straight line of some sorts. All right. So now we want to know. Okay, one of the things we have to understand is: do we make this boundary dotted or dashed or solid? So notice up here, this boundary was dashed. And this was because there was no or equal to here. You see how there's no or equal to? So that means that the line itself is not included in the solution set. But down here, we have an or equal to. So that means that the boundary line is included. So it's got to be a solid line. Okay? So solid line. This or equal to means it's a solid boundary line. Okay, does that make sense? Or equal to is a solid line. So all the points that are on line are included. Okay, so now what I need to do is I need to find out if the solution region is above the line, like over here, or if it's below the line, down here. And what you could do is you could do a test point. Now I have the little definition of a test point down here. I'll bring it up. And this is probably going to be the easiest way to go about this. Pick a point that's on one side of the line or the other, and you use those coordinates to see if those coordinates make the inequality true. And then that will tell you whether that point is one of the ones that's in the solution region or not. So let me demonstrate. So let's pick 0, 0 is always really easy. If that's not on the line, if that's on one side of the line or the curve or the other, pick 0, 0. Super easy. Because if I test 0, 0, it's going to look like this, right? 3, 0. Now what's my inequality? Less than or equal to 6. So 0 plus 0 is 0 less than or equal to 6. Is this a true statement? Yeah, 0 is less than 6. So guess what? The solution region is below the line because it includes the point 0, 0. And what you would literally do is shade with your pencil the area below the line and make sure the line is solid. And that is the graph of the inequality. So that means that all of these points, every point in this region, would be a solution to this inequality right here. That's what that means. Okay? Now that we've done that work, B is really easy because we've already used test points, right? So where is the point -2, 4? Well, if we drew this line carefully, I could kind of see -1, -2, and then up 1, 2, 3, 4. Look at, it's just above the line. And the solution region, remember, was below the line. So is this point part of the solution? The answer is no, it's not. A big N-O there. And again, we could use test point. We could use the test point and find out on our own. We could do it algebraically. So -2 would go here and 4 would go there. That's going to be -4 plus 12. -2 comma 4. 2. -4 plus 12. Okay. Is that less than? Yeah, is less than or equal to 6. -4 plus 12 is +8, right? So is that true? In this case, no, it's not true. That's why it's not part of the solution set or the solution region. Okay? So the one note, if there was no or equal to here, if it was just less than, then this line would be a dashed line, okay? Not a solid line. Any questions right now on this? All right? So remember, the big difference here is if it's an equation, the solutions to the equation are all the points that make up the line. In this case, because it's an inequality, we're talking about the points that are either above the line or below the line usually. Okay? All right. So I tell you what, why don't you take 2 minutes and graph this one on your own. Okay? So do exactly what we just did in that example. Do this one on your own, and I'll show you the answer in a couple minutes. And you can see if you're on the right track, okay? So look back at the other example, do it exactly like this one, and let's see what your answer looks like, okay? Take a moment to do that. All right, so if you had a chance to do that here now, let me explain to you what I did. So you could just do a table of values here, so x, y. You could pick any value. Usually x equals 0 is the first one you want to pick, that's fine. So if you put x equals 0 in here, then you're going to get y equals 0 as well. So you have a point 0, 0. So you're going to want to pick another x value, not 0 for y, because you're going to get 0, 0 again. So pick any other x value, 2, 3, -5, whatever, and find out what the y value is. Then you have the second point used to draw your line. Okay, so that's what I did. I did 3, and you get 3, 6. Now, because this is not or equal to, see, the boundary line has to be dashed. Okay? So it's a dashed line, not a solid line. I did put this up here too because some of you might be thinking, I don't really like this form of a line, or this right here, I don't really like that. If you want to get it to y equals mx plus b, you go right ahead. Just solve for y, and this is what it looks like in y equals mx plus b form. And you can see that the y-intercept is 0, the slope is 2, so you go up 2 over 1, up 2 over 1, up 2 over 1, and you get your point. So once you've plotted the line, the boundary line, now a good idea is to pick a test point. I picked randomly 3, 0, just to test if this side of the line was part of the solution set. So I tested 3, 0, I put 3 in for x, 0 in for y. I got 30 is greater than 0. That is true, so that's what led me to believe that this is the solution region over here on this side of the line. Now, did you guys get this same answer? Is there something I did incorrectly here? Does it look good to you? Yes, don't know, processing. Okay, all right, so that's what that one should look like, okay? Boundary line, test point, that sort of thing. Okay, let's see here. I was going to maybe go over a problem here with you. What I'm going to do is probably save this type of thing for the next lesson. So we won't do this example today. That can be found in your textbook, though. Please take a look at the key ideas. I'll give you your assignment here, and then I'll let you get started on that assignment. Okay, so that's the basics of this lesson. What is an inequality? How do we graph one? How do we use test points to find the solution region? Okay. All right. So take a look at those key ideas. So here's that example, the word problem example. I'll let you take a look at the question there again, and here's the solution in the textbook. And just for sake of time, I'll just get you to look at this. But creating an inequality is important as well, and this example might help you to see that. And here are your questions in your textbook.